Okay, so first thing we do to solve this problem is we draw the free body diagram. And I know that we have the weight, of course, that's the earth pulling down on the car. But in this situation, because the car is on the outside of the hill, I know the net force has to be towards the center. So if the net force is towards the center, the normal force has to be smaller than the weight. So I'm going to draw a pretty small arrow there just to remind myself that it's smaller. So I know it's not in equilibrium, so I do net force equals ma. First of all, I'll go ahead and calculate the weight. I know that the mass was 1,500 kilograms. We'll go ahead and use G as 10, so this would be 15,000 newtons. And when I do net force, I always want to do big minus small. So it would be the weight minus the normal force, and then that equals ma, but since it's a centripetal acceleration, because it's going at a constant speed, it's only changing direction, the acceleration is v squared over r. So I can go ahead and plug some numbers in here. The weight, again, is 15,000 newtons minus the normal force. I don't know what the normal force is. That's what I'm trying to find. When you put in m, make sure you're using the mass, which was 1,500. If I slide up, it tells me that it's going at a speed of 20 meters per second, and I can see that the radius is 60. So make sure you take the 20 and square it, divide it by 60. So you solve that for n. So I went ahead and calculated this number over here. The net force is 10,000. That means the normal force and the weight are going to be different by a total of 10,000. So that means the normal force is only 5,000 newtons. It is significantly less. And again, that's why you might fly out of your seat just a little bit as you go over the car, or as the car goes over the hill.